We've heard how astronomers have learned how to correct for or cheat the atmosphere and thereby deliver much higher angular resolution to a telescope than would otherwise be possible. There's a second method that can be used to attain extremely high angular resolution in astronomy. It's called interferometry. With an interferometer, the light from separate telescopes are combined as if they were one large telescope. This does not give you the collecting area equivalent to that one large telescope, but it does give you the angular resolution suitable for the largest separation between the elements. This can be gain a factor of hundreds or thousands over the angular resolution of a single mirror. The key requirement of this technique is that the waves have to be combined coherently, which means their phases have to be preserved, which means extremely accurate registration in space and also in time. Now this trick is better done at radio wavelengths and optical wavelengths, because the waves, the radio waves being used, are billions of times larger than optical waves. So radio astronomers have been using this technique routinely for decades. In optical astronomy, it's just emerging as a technique. The classic example of interferometry in astronomy is the Very Large Array, located in New Mexico. If you fly across the western United States, from Texas to California, you're quite likely to fly over the Very Large Array near Socorro in New Mexico. It's easily visible from an altitude of 30 or 35,000 feet. What you will see is 27 dishes, each of which is 15 meters across, spread on a Y-shaped pattern on railway tracks that extend for dozens of kilometers through the New Mexican desert. These dishes are having their signals combined automatically to recreate the effect of a 26 or 27 kilometer wide radio telescope. A frontier facility that's going to do this at millimeter wavelengths, which has never been done before, is the Atacama Large Millimeter Array, or ALMA. This is currently being built on an extremely high site in northern Chile at an altitude of over 5,000 meters, which is an extraordinarily difficult place to do either engineering or astronomy. The altitude there is required for the dry air that is needed for transmission of millimeter waves through the Earth's atmosphere. Optical interferometry is a new and much more challenging technique because the waves must be registered to within a tiny fraction of the wavelength of visible light. That's a very small distance. The pioneering facility here is the Keck interferometer, whereby the twin Keck telescopes, who spend most of their time observing different astronomical targets, are combined and look at the same target. Each is a 10-meter mirror, but they're separated by about 50 meters on the summit of Mauna Kea. So in the Keck interferometer, these waves are combined. If in addition you can correct for a point source, you can subtract off that point source and see very faint residual light at a level of 1 part in 100 or a few hundred million. That's the way astronomers hope to detect Earths, by direct imaging, a very exciting technique. Radio astronomers have been using interferometry for over half a century. In fact, they even launch radio telescopes into space so that the baseline of the radio interferometer can be larger than an intercontinental baseline. The limit of the angular resolution by this technique is 1/10,000th of an arc second. Incredibly high angular resolution. That trick has not been possible at that level for optical astronomy, but that's the hope and that's the prospect. It's interesting to see what an angular scale of 1/10,000th of an arc second actually corresponds to.
What is an angle of 0.0001 arc second? First, picture angles of 45 degrees, 10 degrees and 1 degree, and look at the diminishing space between the endpoints of the closing lines that form the angle. To picture an angle of 0.0001 arc second, we have to go a long way to see the two lines opening at all. In fact, all the way from Paris to New York City. 0.0001 arc second is the angle of Lincoln's eye on a penny in New York City as seen from Paris.
To sum up, interferometry is an exciting technique for combining the light from separate telescopes as if they were part of one large telescope. A technique routinely used in radio astronomy and increasingly used in optical astronomy too. The ultimate limit of this technique is an angular resolution of a 10,000th of an arc second.